Am I audible? Let me know if I must increase my volume or something. Okay, my voice is low. I suppose someone said low. Okay, now how do I know if I am speaking loud enough? How will I know that? And by the way, I will be 1 minute ahead of you guys. So if I'm speaking something, it means it's going to reach you like 30 to 40 seconds later. Just send me a message, like if the voice is fine, then I'll start with the thing. Shashank is typing apparently in the group. Let's see. Good enough. Okay, fine. So I'll try to maintain the same volume so that I remain audible. Okay, let's see. Is this screen visible? Is the screen visible? I mean, you'll be able to reply to this after 30 seconds, right? So we'll see. Okay, you can look at this. Let's fine. So keep in mind that if you're listening to anything, like whatever is on the stream is 1 minute behind reality. So there'll be that gap between us. Anyways, okay. So now we'll start with this. Last time, if you've uh, listened to the minor two class, we stopped at class 20, 19, 19. Yes. So I'll be starting from class 20 now. Let's see. I'll be reading these slides for the first time along with you guys, along with most of you guys. So we'll see. Recap. All of this we did in class 19. So the video is still around class 19. You could. Is it 19 or 18? Wait, let me know. Where did we do 19? Did we do 19? We did 19, I think. This is 19. Did we do this? I think so. We did this, right? I remember. We did this. We did 19. So 20 it is. Okay, this is whatever that was done in class 19. Fine. Search direction, step length, stopping condition. Okay, see, search direction is basically. Can I write on this? Search direction is basically the P, if you remember. Step length was alpha. Stopping condition, there were three conditions, right? One is checking if uh, we'll come to that. There were three conditions, if you remember. Good for you. One was about same x values, the other was about function value is same, the other one was if gradient is almost equal to 0. There were three conditions. It is a part of minor 2 syllabus. I think it may appear later as well. Let's see if it will appear later. Observations. Okay, this was computing alpha. Anyways. Okay, what is all this? Given f of x, iterate x, xk at iteration k. Okay. There is some function f of x1 comma x2, and that is some scalar function, direction p. Okay, this is gradient descent, right? If direction is negative of gradient, it's gradient descent. That is fine. And then what else is it? Compute step length. This was done in class 19. You may go have a look. This was done in class 19. How do you find alpha? Then x2 is equal to x1 plus alpha 1 p1. It's just iteration. That is fine. Then optimality. Basically, when do we terminate our thing? Here they're checking if the function values are almost equal. So this is some epsilon. Epsilon we will decide what it is. All of this is it's in class 19. Maybe when we come to class 19 we'll see. But this is the termination condition that is basically checking if the function values are close to each other or not. Fine. This is all recap. Is there anything new here? There's nothing new here. Okay, here you got x2, so you restart the process. To whatever you did on x1, now you do the same thing on x2. Okay, they're giving us some example. Let's see. There is some scalar function. They gave a starting point. Now what is this method? Here, if you look at the example, they're taking p as negative of gradient. It means this is gradient descent method, which was in the previous slides. So we're still discussing the previous slides now. Gradient descent method, find p, then your x2 is nothing but x1 plus alpha plus p. We have x1, we have p, we don't have alpha. So our x2 will now be a function of alpha. Since x2 is now, see you can see here, x2 is now a function of alpha. If I substitute x2 in this function, if I substitute this x2 in this function, where is the function? If I substitute in this, I will get my f of x2. Now I'll have to differentiate this f of x2 with respect to alpha, so that I'll be getting my alpha value. Differentiate and equate to 0. Why are we doing that? Because uh, we are going to get the extreme value of f of x2. If the derivative is 0, if the derivative is 0, it means you're going to get an extreme value. Extreme in the sense it is either minimum or maximum or it's a saddle point. Here, since the function It's like minimize, so you will get minimum. But how do you verify this? If you want to go like deeply, you just take the double derivative and check if it is positive. If the double derivative is positive, that means the extreme value that you got is minimum. But here they're not doing anything, so it's like it is fine. Just take derivative, equate to zero. Whatever alpha you get, that is your uh, alpha. That is your answer. So that will be your step length. This is basically what is this? Gradient descent. A descent because negative of gradient. You are going down the slope, so negative. That is fine. So this is also fine. Finally, you'll get your x2. Okay, now how do you check if this is optimal or not? I told you there were three conditions, right? In the previous case, what were they checking? In the previous case, they were checking if the function values are same or not. So you take the difference of the functions, take its modulus, and check if it is greater than some epsilon. Mm, Here they told one more example with different stopping criterion, right? So here they're checking if the gradient is almost zero. So what they're doing, they're taking the magnitude of the gradient and checking if it is smaller than some epsilon. This epsilon will be a very small number. So this is basically checking if the gradient is almost equal to zero. Here, what is the epsilon that they took? Okay, let's see, where is it? Okay, they're not showing the calculations, are they? Where is the epsilon? Okay, they did not give the epsilon, but it's fine. I don't know. If you look at it, just let me know. This epsilon is going to be a very small number. So just take the gradient of f of x2, find its magnitude, and check if it is, let's say, for example, it can be 0.05. If it is not less than 0.05, then you continue with the process. Get x3, check the gradient at x3, check if the gradient at x3's magnitude is less than epsilon. If it is less than epsilon, then it's fine. You can stop here, or else you have to continue. Find x4, and then it goes on. Fine. This was also in slide 19, PPT 19. Example, minimize so and so. Okay, now three dimensions. You have three components. Gradient descent method, simply find negative of gradient, you'll get your p. Substitute the p in this one. Basically, xk plus 1 is xk plus alpha k plus pk. We have xk, we have pk, we don't have alpha k. So xk will be a function of alpha k, which is this one. Everything is in terms of alpha. Substitute this alpha in, substitute this x2 in the function, you will get some function in alpha. And mind you, capital X and small x are different. Capital X is the point, small x is the component. So here what you will find is uh, x1 is nothing but let's say small x1 comma small x2 comma small x3. So careful. This is a point. This is a point. These are components. So don't get confused. So point in the sense this is basically a vector. But all of these are scalars. They're all numbers. Careful over there. Fine. So all of this is still gradient descent method. Mm, okay, so they're giving us examples, showing us why finding alpha is difficult. Because if you notice, when you substitute your x2 in the function, you will get some big function like this. Big in the sense it has cubes and squares and all of that. If you try to take the derivative, you're getting something like this. Now you have to equate this to 0 and then Any messages? No. Okay. Equate this to 0 and then find the roots, which is very difficult. It looks difficult. It is tedious. That is what this slide is trying to tell. Mm. So they want to propose a new method. Let's see what it is. Backtracking line search. Generic steps. Initialization. Start with an okay. They're saying you simply guess your initial step size. Okay, let's see. Condition. Select alpha such that the objective function decreases sufficiently. Okay, maybe now we'll be going through these conditions. Armijo, Goldstein, and Wolf. Let's see. Backtracking. While a certain condition is not satisfied, reduce the step size. Okay. Okay. The backtracking line search terminates when the condition is satisfied. So here basically what is happening is you guess the initial alpha. You basically guess it. And then using one of these conditions, you check if your optimality condition is reached or not. In case if you say you're using Goldstein condition, let's say the condition says the optimality condition is not reached, then you repeat the process, but now your new alpha will be let's say your new alpha will be the old alpha times beta. Beta is a constant, and beta will be in between 0 and 1. So we will be decreasing the alpha that you guessed initially. We'll keep decreasing it by multiplying it with this factor beta, because beta is less than 1. So it means your new alpha will be smaller than the old alpha. Your alpha keeps decreasing. So that is how it goes. Finally, one of these conditions will be satisfied, this Armijo, Goldstein, and Wolf conditions. Then we can terminate our process. This process is called backtracking line search. You guess the alpha. We'll see. Uh, this was what we were doing previously. Uh, what is this? Finding the minimum or maximum? Minimum. Okay, fine. There is an f of x. They will give us a starting x value. Then we have to find p. P is not. Okay. P is nothing but the direction. Alpha is nothing but step length. All of that we did. All of this we did. Mm, it's the same process, but the only thing that's different here is you are guessing your alpha, and there is some other constant called beta, and there are new conditions which we look at. Let's see. Okay, whatever we were discussing is here. There is a beta as well. Beta is a constant. You guess your initial alpha, check if it satisfies the conditions. If it doesn't satisfy the conditions, then multiply alpha with beta so that you get your new alpha, and then check the conditions again. Keep repeating this until the conditions are satisfied. And if the conditions are satisfied, then you can proceed. You can be like, I got my new x2. So from x1 we'll get x2 using this procedure, which is called backtracking line search. The rest is the same thing. Rest is the same in the sense now you can check if the function values are almost same, or if the x values are almost same, or mm, if the gradient is almost 0. Let's see if that is what they did. The only change here is we are guessing our alpha and multiplying it with beta. That's the only difference here. Backtracking, Armijo condition, these conditions will determine the appropriate step size. Fine, let's see. Okay, Armijo condition, something is here. The function value at this is nothing but xk plus 1, right? This is so f of xk plus 1 must be less than f at xk plus something, m1 into alpha into pk dot gk. Okay, let's see. Maybe we'll look at it. look at an example. When the R major condition is satisfied, a step size is found that guarantees a sufficient reduction of f such that this reduction should be proportional to both the obtained step size and the directional derivative. Interesting. What is this? This condition, R major condition, ensures something. That's why we're using it. You can read what does it ensure. It's like sufficient reduction of f. Since this is a minimization problem, we want to reduce f. So it is somehow telling that if this condition is satisfied, f will be minimized. That's it. There is nothing much in this. How did we get this condition? We are least bothered. At least from the exam perspective, we don't need to know where did this condition come from. Goldstein condition, where is it? Maybe, okay, they've given it a separate page. I wonder what is this g of k. P of k is my direction, I get that. What is g of k? We will see. Maybe they'll give us an example. Maybe then we'll be able to see what is g of k. What is g of k? M1 seems to be like a new constant, so we'll look at that as well. What is M1 and what is GK? Others we know. Alpha we are guessing, and GK we'll have to see. We'll see. Goldstein condition, there is a separate slide for that. Wolf condition, the curvature condition is required to guarantee that the directional derivative at the current accepted point is greater than the product of the directional derivative at the previous accepted point and a constant factor. Okay, let's see what does it mean. Okay, let's see. Okay, let's look at Goldstein, whatever it is. Uh, wait, now are these three conditions the same thing though? Wait, is it lagging? Let me know if the video is lagging or something. Is the video lagging? Is the video lagging? Okay, the video isn't lagging. Okay, anyways, where was I? Now that I'm thinking, they've given this one condition. Maybe all these three conditions are the same thing. Maybe let's see. For a step size alpha, G1 is this one, G2 is this one. Oh, G1, what is G? Okay, Goldstein 1, Goldstein 2. M1, M2 are constants with. Okay, this is okay. M1 is less than this. M2 is the other one. Fine. Maybe it will be better understood with an example. Let's see. So we have two conditions in Goldstein. Our condition looks very similar, suspiciously similar. Maybe all of them are like, okay, let's see. Let's look at an example. Okay, let's look at an example. We have f of x. They gave us a starting point x1. We are going to guess the alpha value. Beta is a constant, you fix it. It is beta lies in between 0 and 1, so it's 3 by 4 here. M1 is also like somehow they took M1. If you look at the previous slide, they told M1 is less than 0.5. So M1 is 0.2. Fine. Now they're finding the function value at x1. So look at this. Capital X1 is nothing but small x1 comma small x2. So he's finding the function value at capital X1. Go, go, go. Okay, let it glitch. This is the function value. Then what did he do? He substituted the points, so he got the function value at capital X1 3 by 4. Using gradient descent, this person is finding the direction P1. He got P1 now. Now he's trying to check the Goldstein condition. This is the function value at capital X1. Wait, this is the function value at capital X1. Now he has to add this as well, right? So, okay, let me write it. F of X1 is this one. Alpha 1 is, we guessed alpha 1 to be 1, right? So alpha is 1. P is minus half, comma half. So what will this be? Small x1 is 1 from here. Small x1 is 1. 1 minus half is half. And small x2 is half. Half plus half is 1. Half plus half is 1. Fine. So we have to find this one. This is also equal to 3 by 4. If you want, you can check. This is also equal to 3 by 4. So, and f of x1 is also 3 by 4, which we got from here. This is 3 by 4, this is 3 by 4. And m1 was 0.2. m1 is 0.2. And p1 dot. Okay, so g is the gradient. It looks like g is the gradient, right? G is the gradient. So, okay, let me write that. G is the gradient. G is gradient. Gradient at point xk. M1 is some constant, M2 is some constant. Alpha is the step length that we guessed, that is fine. Xk we know, Pk also we know. Okay, now Goldstein condition is fine. Now there are two conditions, right? If it is minimization, I think we will use G1, and if it is maximization, we'll use G2. Yes, so we'll use this for minimization. Maximization, I think we'll use this. Let's hope I'm right and we'll proceed. So what is the problem here? All of, oh, let me keep this up. P1 was something. Gradient at F was the same thing. No, P1 and these two things are the same thing. So I just have to find minus half into minus half will be okay. So that is the problem here. So 3 by 4 less than 3 by 4 minus 1 by 2 is not satisfied. So Goldstein condition is not satisfied. If you want, you can do the math again. I basically substituted things in the first G1. I don't think I think G2 is for maximization, but we are solving minimization problems. And I think all the conditions are the same thing. They're all, everything is the same. I think Armijo, Goldstein, and Wolf are the same things. I don't know, but let's see. It looks like it's the same thing. I don't see three different examples. Let's continue. Since it's not satisfied, then we continue the same process. Alpha is reduced by a factor of beta. In the sense, my old alpha was 1. Now my new alpha will be alpha 1 into beta. So 1 into 3 by 4 will be 3 by 4. So my new alpha is 0.75, which is 3 by 4. Beta is always constant. M1 will also remain constant for some reason, so it's just 0.2. Repeat the process altogether. P1 will give you a direction which using what is it? Gradient descent method. We are taking the negative of the gradient. Condition G1. Okay. Okay, so fine. I take my words back. You use both of them. My goodness. They're using both the conditions here, G1 and G2. Hmm. Fine, they're using G1 and G2, so careful. Where is M2 though? Here there is M2, right? G1 condition is satisfied, that is fine, you can do the math. M2 is okay, there's this formula. Okay, great, nice. Here it is there, right? M2 is 1 minus M1. Keep that in mind. So fine, okay. Goldstein conditions, okay. I'll give you a clarity. G1 is there, G2 is there. These two are Goldstein conditions. Xk is our current point, alpha is the step size that we guessed, pk is the direction, uh, xk I told you the current capital X value. M1 and M2 are constants. M1 M1 is less than 0.5, M2 is nothing but 1 minus M1. Pk is the same thing, the direction, Gk is the gradient. So pk dot gk, all of this is fine. So you have two conditions. If one condition fails, you can say it failed and then find the next point. If both of them are satisfied, let's see what's going to happen. Here G1 is satisfied, G2 is also satisfied. Okay, so if both of them are satisfied, then you can say the whatever alpha value that you are at currently is the alpha value. So the alpha value that we are at is 0.75. So that the current alpha value is 0.75. So you return 0.75. All of this we did only to find the step length. We only found the step length. Okay, so okay, now I got my answer. All the conditions are different. Goldstein condition is different from the other conditions, but they do look similar. Let's see. Hmm. What is similar? W1 is similar to G1, right? W1 is very similar to G1. Only W2 is different. W2 is different. How is it different? Hmm. This is the direction. PK is the direction. This is the gradient. F dash is the gradient in that direction. Which direction? Gradient at xk plus alpha pk. That is fine. How is it different from this? It's just conditions at this point. You just have to remember the conditions. Which condition is associated with which name? So Goldstein, you have G1, G2. Wolf conditions, you have W1, W2. W1 and G1 are the same things. It's the same condition. W2 is different, but all the other things are same. M1 is less than 0.5, M2 is just 1 minus M1. Okay, they did mention W1 is same as T1. Fine. Sufficient decrease condition. Okay. Step results in sufficient reduction. Okay. Second condition is called curvature condition. Okay, fine. Some theories there. Maybe you could just go through it. What is the sufficient decrease condition? What is the curvature condition? Because in minor 2, ma'am just ask some random theory questions, so you could consider this as a theory question. What is the Armijo condition? What is the Goldstein conditions? What is sufficient decrease condition? So bear this in mind. Common choices of alpha. Okay, I didn't look at Armijo condition. There's this Wolf condition, there is this Goldstein condition. Maybe Armijo condition is just this basically one line. So G1 and W1, maybe that itself is the Armijo condition. It looks like that. Armijo condition is basically G1 and W1. Goldstein conditions, you have G1 and G2. G2 is just the reverse of G1, but now instead of M1, you will have M2. Uh, this is one example. Wolf condition, instead of in the Goldstein condition, replace G2 with W2. Some new thing, you'll have to remember this. Its meanings are explained here. You could go through them. Common choices of alpha. Hmm. Simplest tool to implement. Okay. What is it trying to tell? Diminishing step size. Okay. I mean, these this slide is about in this slide is talking about different ways of choosing alpha. What we looked at is backtracking line search. That is what we looked at. How to find alpha. These other these are the other ways of finding alpha. Constant step size is for each and every iteration you fix your alpha. That is the constant step size. Diminishing step size is for every iteration you keep reducing the step size. For example, if you look at this, as the number of it, k represents the number of iterations. As the number of iterations increase, alpha keeps decreasing. So that is one way. So constant step size, diminishing step size. Uh, what we did right now is backtracking line search. Backtracking line search has Armijo, Goldstein, and Wolf conditions. That is what we did just now. Okay, end of class 20. Let's see if I got any messages. No messages, fine. What is in 21? Search, backtracking, and things. Yes, we looked at all of this. There was nothing much. Is the video lagging? It feels like the video is lagging. Is the audio lagging too? Let me just ask you guys. On my screen, it looks like it's lagging. I just sent a message. Let's see. Okay, no, I guess. Okay, you guess. Are you not in class then? Okay. I'll suppose everything is fine because I'm sitting in a room and the connectivity is not that nice. Let's continue. Backtrack. We looked at this. All of this was done. We looked at this slide as well. Goldstein, we know. Wolf also we know. W2 is different. This also we looked at it. Fine. What is this? Gradient descent. PK is negative of the gradient. That is fine. That is gradient descent. Where is this? Basically, PK is nothing but negative of the gradient. So the dot product will be less than 0, right? Because gk dot minus gk will be less than 0. That is what they wrote here. That's why this condition is there. And you wonder why the transpose is there over here. Well, time for vector calculus, vector or whatever you call it. So I can represent vectors using matrices. So if I have, let's say, let me take x. If I have x bar, which has like x1 and x2, I can write this as x1, x2. So any vector can be represented as a column matrix. And now that I can represent, okay, let me keep this here. Now that I can represent vectors as column matrices, how do I represent dot product of two vectors? So A bar dot B bar is nothing but A transpose B. If you convert A bar to its column, uh, matrix and b bar to column matrix, you represent the dot product of two vectors in this form. That is why there is a transpose appearing there. So this is matrix notation. That's it. Vector notation means you can directly write a gradient of f, gradient of f at xk dot pk is less than 0. This is vector notation. If you're not using vector notation, if you're using matrix notation, this is how it's going to look like. So bear that in mind. That's why transposes keep appearing everywhere. Okay, we did backtracking in the previous class. This class will be doing something, it seems. That is fine. Okay, and yes, optimality check is these three conditions. So there is no change in x value. So you look at x2 minus x1 and take its mod and check if it is less than an epsilon value. No change of value means you check if the function values are almost same. Take the mod and check if it is less than an epsilon value. Gradient n to 0 is just take the magnitude of the gradient and check if it is less than some epsilon. That is also, we looked at all of this. Limitation of gradient descent. Limitation of gradient descent is basically the problems. So what are the problems that we get with gradient descent? The problem is gradient descent will keep giving you nice things, but suddenly, not suddenly, slowly over time, stars. What is it? You will satisfy these three, any of these three conditions even before you reach your optimal point. That is because epsilon is a small number, and we are saying that if difference in x or difference in f of x, or if the gradient of the function is less than an epsilon, then you stop, you can terminate the process. But sometimes the graph may look like this, and you may reach your termination here itself. So that is the problem here. So unless your and if you keep decreasing your epsilon, then the computation also increases. uh, you get my point, right? So that is the problem. The smaller is the epsilon, the more number of iterations that you're supposed to take. More number of iterations means a lot of computation, because we want our epsilon to be tending to 0. That is why we are using an epsilon. Theoretically epsilon should be 0, but we can't we can't do that. You can't find it will be computationally expensive to find exact optimal point. All of these are just approximations. How do I approximately find the optimal point? And this sad fellow is like, it's like stuck, he's stuck in some local minima, but he's unable to go to the global minima. So those are the problems with gradient descent. Let's see. Okay, Rosen, there's some Rosenbach function, steepest descent. Okay, this is just an example. There's nothing. It's just an example. You do gradient descent. You keep going, 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 going. But optimal point is here, but you're not reaching. You will go. You will reach the optimal point when you keep decreasing your epsilon. But as you keep decreasing epsilon, your computation, the expenses, it keeps increasing. Okay, some new concept, second order methods, Newton's method, conjugate. Okay, let's see what are all of these. Let's see. Newton's method. What is changing? Okay, the only thing that's changing is finding alpha, right? So let's see. Everything else is same. Everything else is same. I think. Okay, not alpha. We are changing p. Okay, let's see. In gradient descent, we simply take the negative of the gradient. That is fine. In Newton's method, what are we taking? H is the Hessian, right? I think. Let's see. I'm guessing it's the Hessian. I'm guessing it's the Hessian. So you take the negative of the inverse of the Hessian of the gradient. Is that what it is trying to tell? Maybe. Hmm. And it becomes quasi Newton if you replace the inverse of the Hessian with some b, where b is an approximation. Fine. Is there anything else? Conjugate gradient. Conjugate gradient. Okay, you will take the negative of the gradient and you add something to it. You add what you add to it. You add the previous direction. You add a multiple of the previous direction. The beta k is a scalar. Fine. So it's like the current direction depends on the previous direction. So that is conjugate gradient. Fine. So all of this is fine. Here we are changing p. Alpha is not changing. Here p is changing the direction. Fine. Let's see. Why do they perform better? And okay, so Hessian. I think H is the Hessian because Hessian is a second order. It uses second orders, right? Second order derivatives. It would look like this. This is the Hessian. So Hessian of a function is okay. How do I write this? Hessian of let's say Hessian of x1 comma x2. Let's see. This is nothing but a matrix uh, dou square f by dou x1 square dou square f by dou x1 dou x2 dou square f by dou x2 dou x1 dou square f by dou x2 square. This is the Hessian matrix. Mind you, just check the order in the denominator, but I think these two quantities will be the same. They will give the same value. So it means this is a symmetric matrix. Yes, this is a symmetric matrix most of the times. This is the Hessian matrix. Since it's a matrix, you can find the inverse of it. So they're using the inverse Hessian matrix. That's it. Nothing much here. They perform better because they're using second order, and that's it. There's nothing much here. Okay, they try to explain it intuitively. It's like in every iteration, if you're using the gradient descent or whatever, it's all linear. So you keep going like this. It's not smooth, but second order is kind of smooth, so you get better results, something like that. Linear approximations are very rigid, straight, so it doesn't work well with smooth functions. Maybe that is an intuitive explanation. Let's see. Newton's method. What is Newton's method? You have okay. Use capital X so that you don't get confused. Or else, if it's one dimension, you can just use small x. But in n dimensions, you will have capital X, which is nothing but x1, x2, so on till xn. This is an n dimensional vector. We've seen three dimensional. We've seen other dimensions as well. Okay, moving on. So new point is nothing but old point plus uh, it was alpha k pk, right? Is there no alpha k here? Maybe they're taking alpha k as one. I see pk, but I don't see alpha k here in this case. Let's see. We call the inverse matrix. Okay, inverse do not always exist. If the inverse doesn't exist, then there may be no solution. Okay, computing the inverse can be expensive. Yes, computing the Hessian matrix itself can be expensive. Yes, Fine. I think in this line they must have considered alpha to be one, but it need not be one. Let's see. Let's see if it. Let's see if Newton's method requires us to take alpha as one. Let's see. We'll not jump to conclusions. But we've seen this. This is the negative of the Hessian, and then multiplied with the gradient. Fine. Let's look at an example. If there's an example. Okay. No example. Let's wait for a quadratic function with positive definite Hessian. And if you remember in the previous classes, we've seen how do I know if a function is how do I know if a function is convex? Convex means looking like this. Function is convex if the Hessian of the function is positive semi-definite. Maybe we'll come to that when that slide comes. It was there in uh, slide PPT 18 or 19, somewhere over there. Positive definite. Okay, rescaling the gradient. Okay, if objective function is convex but not quadratic, this update can be iterated, yielding the training. Okay, Newton's method is appropriate when Hessian is positive definite. Deep learning, the surface of the earth is generally non-convex. Okay, something it's telling. Some information, maybe you can just look into it. So maybe usually we'll use this when Hessian is positive definite, we know that the function is convex. And if the function is convex, it means we are usually searching for a minimum. So it means, in other words, Newton's method is used generally to find the minimum of a function. So we'll only find we'll use these things for minimization problems. Mm, okay, I think there's a comparison here. The comparison here is okay. Maybe it's like gradient descent is taking a lot of time. Okay, what is gradient descent? It takes p as negative of the gradient, right? And gradient is, if you look at these are contour lines. Uh, so gradient will always be perpendicular to the contour lines. So if you notice this black one, these black lines, at every iteration, they're moving perpendicular to the contour line. So this black ones, these black ones are the points that we got using gradient descent method. But Newton's method uses Hessian and all of those, which utilizes second order derivatives. So somehow magically it finds, not magically, mathematically it finds the minimum in less number of iterations. That's why second, since we're using more information now, you're taking double derivatives, so you will reach the optimum point faster. That's why you can see in the comparison, Newton's method is performing better. Gradient descent. Okay, okay, yes. Okay, I we are starting here. I think I see a green point. Okay, no animation. Okay, fine. They're not. They're just examples. There's nothing much here. Maybe they were animations. Anyways, maybe if you can open it in a PPT and just you can open it in your devices and see. There'll be some animations here. It's nice to look at, but I don't think it's fine. Okay, fine. Approximate Newton. Computing the Hessian is computationally expensive and maybe difficult. And okay, and yes, all matrices are not invertible, right? If the determinant of the matrix is zero, then you can't find its inverse. So can we approximate the Hessian? Okay, there is something called the secant method. Okay, so double derivative is approximated using this equation. Fine. So go on. Use the sequence of iterates to approximate the second derivative. Double derivative, this is for a function. In two dimension, it becomes Hessian, so there is Hessian. If you notice, epsilon is nothing but 2 epsilon. 2 epsilon is nothing but x plus epsilon minus x minus epsilon. So 2 epsilon is basically the difference between the 2 points, x plus epsilon and x minus epsilon. So I have the Hessian here. This became Hessian. 2 epsilon is nothing but the difference between the 2 points. That became this one. And then you have a difference of the function values at the two different points. Not function value, f dash. So f dash is gradient, f double dash is Hessian. So you got a new equation there. Let me click this. This is nothing but the gradient. Fine. So if you get the basic idea, you don't have to memorize anything. It is very similar. These two equations are similar. So Hessian times the difference of the points is approximately equal to the difference of the gradients at those 2 points. This is an approximation of the Hessian. From here, we'll get an approximation of the Hessian. Okay, let's see. Yes, in the quasi-Newton method, we've seen, right? They replaced the inverse of the Hessian with some b. So basically, they're approximating the inverse of the Hessian. Here we are still finding Hessian, but while finding p, we will use the inverse of the Hessian. Okay, now they want to find a nice approximation of the Hessian matrix. So they're going to iterate this. How do you find a nice one? You just keep iterating until a certain condition is satisfied or until a certain constraint is satisfied. So they're like most popular in practices BFGS and LBFGS. Okay, let's see what is this trying to propose. Newton's method without computation. Okay. Primary difficulty computation of H inverse. Okay. BFGS is something. What is something? It approximates H inverse by some matrix that is iteratively refined. Okay. Once the inverse Hessian is updated, the direction of descent is determined by okay. Okay, a line search is performed. Okay. So some procedure they're using to approximate H inverse using some matrix. Let's see if they've given okay. It's just theory. They're not giving us anything. Fine, that is just theory then. I thought they're going to show us how they're approximating or something. But they're not showing us. The idea is you keep iterating until this constraint is almost satisfied. That means you got a um, nice approximation of a Hessian. Fine. They're not telling us. They want to keep it to themselves. So fine. The last method we've seen was a conjugate gradient method. If you remember, where is this? Here, gradient descent we know. Newton's method. Instead of simply taking gradient, you're also multiplying it with Hessian. Mm, Quasi-Newton is you replace Hessian, inverse of the Hessian with an approximation of the inverse of the Hessian. Conjugate gradient, we will see, it's like the current direction depends on the previous direction. When k0 is basically you did not start, right? If you like, you have the starting point, but you don't have the previous point, so there is no previous direction. So if there's no previous direction, you can't add anything. But if k is greater than or equal to 1, it means when I have x1, there will always be an x0 behind it. So I can find p0. That is the idea here. For for iterations greater than or equal to 1, you will always find a point before it. So I can directly, not I mean, I can write this. Previously, I can't write it. That's why they wrote it this way. Beta is some constant. Let's see. Let's see if there is any significance. Let me close the brackets. Okay. Or let me close it here. Okay. Fine. So my new direction is basically gradient, negative of the gradient, plus beta power, not beta power k, I think the kth beta or something. Some constant times the previous direction. Let's see. Okay, yes, that is what is written here. Gradient descent. What is happening? You are here. Okay, red is a gradient. Gradient descent is you go opposite. You keep going, then you keep going, and so on. Fine. This is what happens, right? This is how you move graphically, at least. Conjugate gradient descent. So at x0, you there is no previous direction, so you simply go in the direction that is opposite to the gradient. Now that you're here, this is the negative of the gradient at the point, and the previous direction is this one, right? So maybe I think this graph is not that nice. Okay, I'll look at here. I look, maybe it's nice over here. So at x2, okay, the graph is not updated. It's the same thing. They did not update it. Did they? Okay, they did not update it, so it's fine. And okay, I'll talk about what's going to happen at x2. Wait, sorry. At x2, there is you have two things, right? How do I write p3? P3, is it p3? Yeah, p3. How do I write p3? P3 is nothing but negative of the gradient, which is this one, plus some constant times p2. P2 is this one. So you have a new direction. That's it. You just have an extra term there. That's it. The extra term is you have this one. It is just gradient descent, but now you have an extra term, which is nothing but some constant times the previous direction. Okay, conjugate directions. What is this? Orthogonal directions. That u and v denote two vectors. Okay, they're said to be orthogonal if their scalar product is zero. Okay, you know this. I can say I cap dot j cap is zero. So they're orthogonal, right? Conjugate directions. Similarly, u and v are said to be mutually conjugative with respect uh, to a matrix A if U and AV are mutually orthogonal. Okay, now, this whole matrix. If conjugate directions to the Hessian are used to any quadratic function of n variables that has a minimum. Wait, is this even English at this point? If conjugate directions to the Hessian are used to any quadratic function of n variables that has a minimum, can be minimized in n steps. Fine. Whatever does it say? Okay, conjugate directions. What is a conjugate direction? Let me just see. Conjugate direction. It's basically whatever is satisfying this. Maybe if I represent my vectors in terms of matrices, my problem will not be there. There'll be no problem, I think. No, I think that then there will be no problem. Because now you're multiplying a matrix and a vector. So that is what is itching me from the time since the time I've read this. Maybe we'll look at an example. Maybe then we'll see. I'll think about this. We'll see. Conjugate gradient method. Select initial point, find. Starting me direction is this one only. Directly gradient descent. But if k is greater than or equal to 1, you will get this additional term. Okay, now they've shown what beta is. This beta is the ratio of uh, the magnitude of the current gradient divided by the magnitude of the previous gradient whole square. That's it. That is a constant. Step 3, find step length. Okay, how do you find step length? They've given some big formula over here. What is this? So this is basically okay. If you remember, I told if something transpose, some matrix transpose multiplied with matrix, I can represent it as vector. So this is nothing but gradient of fk dot gradient of fk by pk pk. Okay, there are three over here. I fine. I can't represent the denominator in the form of vectors. Someone can, I can't. There are three quantities. So H is the Hessian. H is the Hessian over there. Interesting. Okay, fine. So you have alpha as well. Alpha is the step length. This is a scalar quantity. After you compute it, you'll realize it's a scalar quantity. You have many matrices, vectors, and things going on, but at the end, it's a scalar quantity. Fine, we got our direction, we got a step length, update new point, test optimality. How do you test optimality? We've seen those three conditions, right? X values are almost same, or f of x values are almost same, or if the gradient is almost zero. There were three conditions. Different ways of determining beta. It is known that choices of the kth beta at the kth iteration. Okay, oh, nice. So many research. Okay, so many things happen. Okay, all of this is there. Fine. We are using some beta. This is some beta. I don't know what is this beta. It may be one of these, but I don't know. Some beta that is. And we are not looking at them, are we? We are fine. Family of CG methods. What is CG? Okay, CG is I think this one. CG is a conjugate gradient. Fine. Different CG methods correspond to different choices for the scalar beta. Okay, fine. Okay, they've given. So all of these are different betas. So which beta are we using again? We are using this one, right? We are using this one. It looks like we are using maybe at least similar to that because we are using GK. We are okay GK by GK minus 1. This is GK plus 1 by GK. Okay, interesting. You don't have to remember all of these. That would be tedious. Maybe just remember this beta. That is fine. You don't have to remember. You don't have to remember all of these. Mm, fine. Or do we? Wait. Are they telling us everything? No, no, no. I don't think we need to remember. This was the alpha that we've been using, right? Yes, we are using this alpha. We are using a similar beta. Are we using a similar beta? Yes. So, okay, fine. So, we are using. So, there's a name for this. Fine. These two alphas are same, but these two betas are not same. This beta is fine because we need to use it in conjugate gradient method. This beta, since it's given in this in a separate slide, maybe just read this. Only the denominator is different, right? What is the denominator? You have difference of gradients. Okay, if you do remember, we've seen that Hessian into xk minus xk minus 1 was approximately equal to gradient minus the denominator reminds me of that. But anyways, maybe if you see something in common, you could connect the dots and then remember it that way. But anyways, you don't have to remember all of these though. All of this is not good. This is fine. Conjugate gradient method. Method two. Okay. From steepest descent. Okay, I think now it makes sense, right? This is your U, H is A, this is V. So if U, A, V is 0, then U and V are conjugate. That is what is, that was what is here, right? The problem here is the dot. I don't know if this is the correct representation, but it's fine. I can simply say U, A, V is 0. Or maybe U transpose. Maybe that would make sense. Now it kind of makes sense to me. Fine. If you're using matrices. Example, fine. At last, as an example, minimize something using conjugate gradient method. They gave us f of x1 comma x2. They gave us initial point. What are we supposed to do? Find the Hessian. Okay, you have the Hessian. Hessian is not going to leave you. You got the Hessian. The initial direction will just be a negative of the gradient. You found the gradient. Fine. Alpha 1. Use the formula. You have the formula. You'll get some value. Yes, so you have transpose. Yes, you have transpose over there. Find it, you will get some value. Fine. Where is beta? Okay, there is no beta because this is still the first, this is the 0th iteration, right? I mean, instead of x0, they're using x1. So fine, call it the first iteration. Beta will come later. First step, you won't get beta. Later, you'll get beta. Check optimality. Okay, gradient is. Now they're checking for the exact optimality. If the gradient is exactly equal to 0, then you can terminate the process. It is not exactly equal to 0, so they're moving on to the next iteration. Or else we would have simply checked if the gradient is less than some epsilon, where epsilon is a small number. Here they're checking if it is equal to 0 or not. Fine, their wish. Next iteration. Now from this iteration we'll get our beta. So we have our newly obtained x2. We can find the gradient at this point. Beta is nothing but current gradient by previous gradient whole square. So you will get some value there. My new direction is negative of the gradient plus beta times the direction. What is the direction? P1 is P1, the old direction, the previous direction. Previous direction was what? Where's the previous direction? P1 here. P1 is the previous here. Minus 1, 1 is the previous direction. So gradient plus b some constant times the previous direction. So using this we get the new direction. This is our new direction. So alpha is a step length. There is a formula for that. Just apply the formula. Hessian we already computed. Finally you will get your alpha 2. Now you can peacefully substitute your alpha and new direction. S2 is basically P2. Don't get confused. I don't know why did they use S. Fine, you got your new point. Now they're checking if the gradient is exactly okay. Apparently the gradient turns out to be 0 exactly. So this is exactly an optimum point, exact value, not an approximation, exact value. Okay, another example. Okay, what did we get now? Okay, interesting. Fine. Another example. By using Fletcher and Reeves method. We've been using that, aren't we? The beta. Iteration 1, there is no use with beta, so just find x2. We know the process. They're checking optimality using this condition. Gradient, is it tending to 0 or not? Here it is not 0, so move to the next iteration. Now from this iteration, you'll get your beta. Beta will come into picture. Find. What do you find? You have x2, find the gradient. You will get beta 2. So your new direction is negative of the current gradient times constant plus constant times the old direction. You get your new direction. Alpha 2, there's a formula for alpha. Alpha k, the step length. Substitute, you will get your step length. Here A is nothing but the Hessian. Did we find the Hessian? Yes, we did find the Hessian. Hessian is here. Hessian is here. A is the Hessian here. You get a new point. Check if the gradient is 0. It is exactly 0. Apparently, I'm not checking the calculations. It is optimum. Fine. Okay. Now that they're using this in an example, so remember this beta as well. So you have two betas to remember. One is the maybe in the doubt if there's an opti class later, just ask ma'am, should we remember this beta or not? But since it's used in an example, I'll be assuming that this is also a part of the syllabus. So remember this beta as well. That was the Fletcher and Reeves, and this is a Dai Yuan method. Fine. Numerator is same, denominator is slightly different. Iteration 1, it's the same thing. Wait, what? Okay, iteration 1 is not mentioned here, it's the same as before. Iteration 2, you start using beta, that is fine. You get, you reach the optimal point using this beta as well, fine. So, in the previous PPT, we've seen backtracking. In this PPT, we've seen Newton's method, Cauchy Newton's method, and conjugate gradient method. There was nothing much in Newton and Cauchy Newton. It's just theory over there, I think. Conjugate gradient, there were some questions. Okay, gradient descent. What gradient descent in ML? Fine. Let's see. You have something, 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 something. Okay. You have some data. Now we have to predict something. If I give a new size, will I be able to predict the price? That is the problem here. That is the problem here. If I want to buy a property, see, that is the problem. I'll give you a size. Let's see how much is the price. Can you predict it? That's the thing. Notation, number of examples. X is input. Fine. X is input. Y is output. X comma Y. It is a point, right? Fine. All of this is fine. I don't think there is nothing much on this slide apart from the problem itself. The problem is stated here. Fine. Predicting house prices. Assume that X and Y are related in a linear fashion. If you do that, see, we know line is wait, line is nothing but mx plus c. So that is what they're doing. C is here theta 1, a theta naught. M is theta 1. They're assuming a linear relationship. You can assume higher order relationships as well, but for now we are assuming the relationship is linear. ML task is to find best theta naught and theta 1 from the given. Okay, what do we mean by best? Suppose ML system tells us that the best theta naught is 1 and theta 1 is 0.2. Okay, let's see. We have, we were already given this, we already have this. Prediction, we will get it using this one, theta naught plus theta 1 times x. So we assumed previously that theta naught is 1 and theta 1 is 0.2. Why? We don't know, we're just assuming. And let's see what is going to happen. So square error is basically you take the difference between the y's and square it. Nothing much. So they're showing us how much is the deviation, how much is the error between the actual values and the predicted values. You get some numbers, number. So squared error is basically this quantity. You take the difference of the actual y and the predicted y, take the square of it. Mean square error. You take the squared error and you divide it by 2 times the number of examples. M is here the number of examples, right? How many? What is M here? 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, 8, 9, 10. Okay, here M is 10. So mean square error is half of squared error by M. So however you remember this, just remember 1 by 2M, not 1 by M. 1 by 2M is it. Okay, now what is linear regression, unconstrained optimization? Okay, now what we want to do is we want to minimize the mean square error. We want to minimize the mean square error. So they're using a notation. J is a function. J is a function of two variables, theta naught and theta 1, which represents the mean square error. So yi is the actual y, and this is the predicted y. And predicted y, we know we wrote it as this one. I is basically the ith x or ith y, whatever, however you want to think of it. But this is the actual one. It since it's inside the square, it's fine if I interchange this as well. I can also write this as nothing to worry about it. You can write it that way as well. So this is a function in two variables. The variables are theta naught and theta 1 because yi's and xi's are already they're already there. From the table we can get the values. From the table we can get the values. is predicted. So what is this person doing? This person is taking the partial derivatives with respect to each of the variables. Here the variables are theta naught and theta 1. Differentiate it. What do you get? You get this, you get this. You can verify. I mean, it's simple. You just take the derivative. How do you take the derivative? Uh, when you're taking derivative with respect to theta naught, consider theta 1 as constant. When you're taking partial derivative with respect to theta 1, consider theta naught as constant. Okay, the derivative with respect to theta naught, consider theta 1 as constant. The derivative with respect to theta 1, consider theta naught as constant. Everything else remains the same. If you have multiple variables, consider all of them as constants except the variable with respect to which you're dividing. So if you have something like x1, x2, x3, and so on, and if you're partially differentiating it with respect to x2, let's say, so all of them will be constant except x2. So that is how partial derivative works. I think most of you will know this. Fine. Linear regression. J is convex. J is a function of two variables. So it is a scalar function. It's not a vector because the output is a number. It's not. It doesn't have components. So a function in two variables will look like this. And this slide is telling us if you plot this function, you'll get a convex function. Convex function. That's it. Why convex? Because what is J? I told you J represents the mean square error. So mean square error can be minimized. Basically, I can minimize the error. That means there is some minimum to this function. And if there's a minimum, it means the function that is the basic idea. If you can maximize something, then it should look something like this. This is a concave function. If there exists a maximum, global maximum, it should look like a concave function. But here J is a convex function because I can reduce the error. I can represent it using contour plots as well. I can represent a function of two variables using contour plots. In this case, the color becomes important. If it is red, it means it's above. If it's blue, it means it's below. So minimum is somewhere here because blue is there. Graphical interpretation. Fine. If you plot these values, you will get these cross marks across the graph. X-axis, along the x-axis you have size, along the y-axis you have price. You can plot this simple graph. This is, you can simply plot it. Now the prediction, which is this one, it's a line, so you can represent it. You can represent the predicted values in the form of a line. So how do you predict? Basically, if you want to know, if you look at this, in this table there is no 500 square feet. So I can just go to 500 square feet and see how much is the prediction. This How much is this prediction at 500 square feet? What what is the amount in lakhs? Is it lakhs? Ones, tens, hundreds, thousands? Yes, it's in lakhs. Or 10 lakhs? Ones, tens, hundreds, thousands, lakhs. Fine. So it's above 100 lakhs or something. Oh, 100 lakhs. 500 square feet. Fine. Whatever it is. Interesting. Costly affairs. Gradient descent for linear regression. Okay, what is this trying to tell now? I would like to assume this is the new point. This is the old point. There is alpha, fine, and then there is okay. So this is basically the same thing. We know this one, right? xk plus 1 is nothing but xk plus alpha k p k. Gradient descent means you have a negative of the gradient. So that is what they did here. Here p is nothing but negative negative of, since this is a function in two variables, you will have uh, you can take gradient in two different ways. So what they've done is they've taken this one, and this is what they did. That's it. Which is essentially the gradient, right? This is the gradient of, oh wait, this is nothing but the gradient of J, right? Hmm. And we found the gradient of J here. Where is this? Gradient of J is nothing but, gradient gives out a vector quantity. Here J is a scalar quantity in two variables. So basically what you get is a partial derivative with respect to this one, and then partial derivative with respect to this. So since I told vectors can be represented in the forms of matrices, column matrices specifically, I can write it as this one by, wait, can I shift things up? No, I can't shift things. So I wrote it in the form of a column matrix, gradient of J. That is what is here. Might not appear that way at first glance, but that is what is here. Alpha is just kept as alpha. Fine. Okay, you have more things. Okay, we are halfway through. It's 11:35. Nice. EP. Okay, the line will depend on theta naught and theta one. So depending on what you choose, the line will uh, be that way, depending on theta naught and theta one. Fine. Mm, interesting. Do you think this line is a good uh, approximator or something? Because see, all my points are here, so I would want my line to look something like this. But this line is like, it's no way trying to tell me anything. So that means the error will be too high on this. That's why it's somewhere here. It's not close to this. It's somewhere far away. It means it's not close to the correct line that will approximately tell you what is what. So this is not a good line. This is also not a good line. Let's see. Like what exactly is happening here? We are applying this one. We are repeatedly changing theta naught and theta 1 until something good happens. We'll see what is that something good. Something good in the sense we want to minimize j. We want to minimize j. And I would not call this capital X, maybe I'll just call them capital theta. Because theta naught comma theta 1 is not a point on this graph. The points on this graphs are x1 comma x2. It's not theta. So this is in some uh, other plane, which is this one. This is x. This is y. In some other dimension, in some other plane, you have theta naught and theta 1. So they are two different planes. They are not coinciding. That's why I changed it. It's not x, it's theta. So if I keep iterating, I think there is some condition. It's going to check if some condition is satisfied. Then we can stop. So they will like repeat until convergence. So for convergence, I think there will be a condition. We'll see. So the line is going to a better place. Let's see what's going to happen. So it's going and going and going. It's tilting. It should tilt, right? It's slowly tilting because if you're trying to minimize the error, it means the line must pass through all the training data. It should not misrepresent the data, right? Okay, line is getting better and better. How is it getting better? We've looked at it. We are iterating it over and over again. Okay, line is getting better, 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 more better. Fine. So line is now nice. So this is a nice line. So whatever is the theta naught and theta 1 corresponding to this, that will be the best theta naught and theta 1. This is linear regression. Hmm. How is this happening? Basically, we are iterating it over and over again, which is where is this? This condition. We are changing theta naught and theta 1 repeatedly using gradient descent. And here J is a scalar function of two variables, theta naught and theta 1, which represents the minimum, not minimum, mean square error. Mm, fine, so we're using gradient descent to make all of this happen. ML problem can be much more complicated. Okay, now this is like more than one variable. So you can have other variables such as floor and all of this. And relationship need not be linear. It could be something like this or whatever. And in the case of here only you have like four more variables. So it will become like uh, 4 5 dimensions. You can't draw it. You have to just imagine, or you'll have to use some representations. Something you'll have to use vectors or whatever. But it won't look like this. You'll have to. It will look much more. You can't draw it. You can't look at it. You have to imagine, or you'll have to use some representations because you can't draw 5 dimension or whatever. At max, you can only draw 3 dimensions. Can't draw 4 dimensions, 5 dimensions. But it doesn't mean they don't exist. You can see this itself is a problem that's using like 4 5 dimensions. So you have a function of function in 5 variables, so 5 dimensions. Error may be different than okay. It's like you have other problems, but this is one way of solving it, not a one for all way of solving it. Finite sum optimization. Okay, yeah, there's a mail this time. Let's see. What's the mail? Okay, nice. Finite sum optimization. Optimization problems faced in data set. Okay. Okay. So you have some function and then you're trying to sum everything. You want to minimize this. Fine, whatever it is. If you have an objective function, you want to minimize it, fine. Okay, that's a problem. They have some data, they have a function, they're just summing everything, dividing it by the number of data points. Now, whatever is the final function, they want to minimize it. Hmm. Fine. There is some objective function, you want to minimize it. How do you minimize it? We have ways to do it, right? So gradient of this, what is the gradient of here? J is different now. Here J is not mean square error. It's just that there's some function f, you sum it across n different x's, and then you want to minimize this entire function. We have a new, this is the objective function of finite sum optimization problem. This is a new problem. This is a new problem. It's a new problem. This is your objective function. Why is this the objective function? Maybe just go through it, but this is the objective function. The context is here. You just want to find the sum and minimize the sum for some reason. We don't know what is the reason, but we have to minimize this. How do you find the gradient of this? You just sum the gradients. That's it. There is nothing much here. GD is gradient descent. So what is gradient descent? You have the current point, the next new point. There is the old point. There is some step length. They're using some strange symbol, maybe new, and you take the negative of the gradient. That's why minus is there. Fine. This f is the objective function. Yes, so instead of j there is small f. So now you replace, so not replace, just instead of this you put this. That is what happened. Yes, there's nothing much here. So we have to keep iterating this until we reach optimal condition. This is finite sum optimization. In the previous case, we were reducing the mean square error. Here we are reducing the objective function directly. I mean, previously our objective function is different. Now our objective function is different. Process is the same. The same process. You just keep iterating over and over again. From the past few classes, we are seeing the same thing. It's just you have a function, an objective function. You have a starting point. You have to find step length. You have to find direction. Find the new point. Check if it is satisfying optimality conditions. Same story, but in different flavors we are going through. Linear regression is a finite sum optimization. Okay, interesting. Okay, let's see. We have a function. We have a function. Okay, see, we have a function and we want to minimize the sum of mean square errors, right? Yes. So here we got the context. We got an example itself. What is where is finite sum optimization used? Here we are taking the sum and we want to reduce the sum. So how do we reduce it? We can use. I mean, it is the same. There's nothing new here. So this will be my gradient of j. This is my gradient of j. When they ask you to write the gradient, just don't compute this and this. Write it like this. Write it in a column vector form, or write it like at least like this. At least write it this way. Don't just compute these two and leave it. Write it as a vector. Vector means it has two components, so write it that way. Don't just compute and then leave it without representing it in the form of a vector. To compute the gradient, we need to enumerate all training. Okay, what is the gradient of this? Uses full training set. Find computing the gradient can be time consuming. Okay, if you have like let's say 10,000 data points and things like that, iterating it over and over again will be expensive. Is that what it's trying to tell? Yes, because if you want to know the gradient here, you have to find the gradient for each and every point. And if n is too large, gradient finding the gradient of this one will take a lot of time. That is what it's trying to tell. Approximating the gradient is still useful as long as it points in roughly the same direction as the true gradient. Okay, okay, something new is there. Stochastic gradient descent. Stochastic gradient descent is a stochastic approximation of the gradient descent. The function that writes the return as a sum of differential functions. Fact that we acknowledge that we do not know the gradient precisely, but still only know noisy approximation to it. Okay, let's see if there's any formula to this. Batch traditional GD. Gradient is computed for the entire set of training data. This is what we were doing. We were trying to find the gradient at every point and sum them up. Here, this one. Find gradient at every point, sum them up to find the gradient of our objective function. That is batch, apparently, batch process. Mini batches, instead of finding it for all the data points, you just take a subset and then find for that. That is mini batch. Stochastic gradient descent. Interesting. Gradient is computed by selecting randomly only one training data. See where we have come to. Here you take the sum of all n data points. Here you take the sum of the gradients at some points, maybe 10 or 20 or whatever. Here we'll only take one data point, one, and then declare this is the gradient of the function. Nice, interesting. SGD is very effective in large scale machine learning and studying. Interesting. We'll see. We'll see how is this put to use. Minimum. Okay, this is our what is this? Mean square error. Our objective function is the mean square error. We want to reduce this, minimize this. Batch gradient descent. Batch gradient descent is you keep doing this for every point. So repeat until convergence. So what is basically happening? It's like you are just adding. See, my objective function is this is my objective function. I want to find the gradient of this. Or is there any? Okay, this is the only objective function. Fine. Mm, they said repeat until convergence. Okay, it's like maybe until I exhaust all of my training points, I just keep continuing with this. So it's like if I have one xi comma yi, I initially start with some theta naught and theta 1, right? So I initially start with one theta naught and theta 1. Since I know my theta naught and theta 1, I can find the gradient. So I will get this value as well. And finally, I'll get a new theta naught and theta 1. So that means using this Using one data point, I will get one line, which is nothing but y is equal to theta naught plus theta 1 x. Now I will bring, okay, let me call it 1, 2. This is x1, x1, y1. Then I will bring the other point x2, y2. From the previous iteration, I will get theta naught and theta 1. So that will be my theta naught and theta 1. I will find the gradient. I will alpha. What is our alpha? I think alpha we can. Uh, it's just step length, no? So maybe just take whatever you want. Did we have any example for alpha? No, we don't. Maybe we'll not worry about alpha now. Maybe just take it as some number. Maybe we'll see if there is any way to find alpha. We are currently concerned about p, the direction p. So after you found not found, after iteration 1, in iteration 2, you're using another data point. Theta naught and theta 1 in the previous iteration, the old theta naught, theta 1 value, you will use here, old value. You will find gradient. Alpha, let's say you got somehow alpha. You will get your new theta naught and theta 1. That would mean your line is going to change. If your line is going to change, this will no longer be your line. You will get some new line which will reduce the mean square error. This new line will represent these two data points properly. If you add one more data point, then you will have to repeat this again. So finally, you keep doing this for all m points. If you do this, then finally you'll get a line that is the best fit. It properly represents your data set linearly. So linear regression. This is batch gradient descent. Mini batches, instead of doing this for all of your m training points, you simply take a subset of it. And here it says random sample. So b is a number which is smaller than m. So b could be 10, 20 or something. So only for 10 or 20 points you repeat this process instead of doing for all the training data points. So you will get some gradient. Need not be the exact gradient, but some gradient you'll get using mini batch gradient descent. This is for theta naught. This is for theta 1. So there will be m iterations. It's just a for loop at this point. It's like you have uh, you have theta, which is nothing but theta naught and theta 1 for I is equal to 1 to m. Do this process. What is the process? Your theta cap is nothing but your old theta cap plus alpha p I, where this pi will be nothing but negative of your minim what is this mean square error. That's it. That is what is happening. Maybe this should give you the idea. You initialize it with some random theta naught and theta 1, and then you keep doing this process. Finally, you will get a nice theta naught and theta 1 value. From this, you will get your theta naught and theta 1. That is batch. You do it for 1 to m. Mini batches, instead of doing it for all values, you randomly pick some data points. Here they're taking 3. It means out of n data points, they're only selecting 3. Is that what they mean? Because I see 3 mini batches. No, no, no. I think there are two examples. This is one mini batch, this is the other mini batch. Is it? Yes. Okay. So uh, it looks like this. So what you do is, hmm, fine. Now, batch size, everyone I think must have understood. Mini batch is something like this. You keep, let's say B is 3, you keep picking 3 data points from your data set and then find the gradient for that. We in batch gradient descent we went through m iterations. In mini batch, let's say uh, how do I say this? Hmm. Fine, you have like 1 to n points. You just pick some b number of points. Using those points, find the gradient. Using the same procedure that we saw before, which is this one. This is the procedure to find the gradient. Gradient in the sense, not gradient, but theta naught and theta 1. And we know how to find the gradient of j, right? This was the formula, if you remember. It was 1 by m times something and something, which is here. Maybe, okay, is there the slide over here? Right, wait, no, sorry. This differentiate this, you will get gradient of j. That is fine. Hmm. Okay, I was telling what is mini batch, no? So you randomly pick b data points. Using those data points, find the gradient. And now you pick some other 3 points, find the gradient. I think it goes on that way. I think it goes that way. In the sense, let's say 1, 2, 3, I will pick. Next, I'll pick 4, 5, 6. Next, I'll pick maybe 7, 7, 8, 9. From here, I'll get one gradient. From here, I'll get one gradient. From here, I'll get one gradient. I can stop if the gradient doesn't change much. So I don't have to use, let's say I have 100 points. Here in mini batch, my batch size is 3. So I will keep collecting 3 points. I will keep getting different gradients. If my gradient doesn't change much, it means I can stop with this iteration. So I think that is what they mean until convergence. So you keep taking batches of size 3 and try finding the gradient. Or in this case, why am I saying gradient? You're trying to find theta naught and theta 1. In stochastic gradient descent, you can think of it like a mini batch of size 1. Mini batch of size, batch size 1. So it means you randomly pick a data point, find theta naught and theta 1. Then again you randomly pick uh, another point in the sense uh, x I and y I. Keep randomly picking this, find new theta naught, theta 1. You keep doing this uh, until your theta naught and theta 1 doesn't change much. It means it almost got converged, so you can stop. Apparently, this procedure is faster because you're not going through all n data points. Only some points you're going through. I think this is what they're trying to tell, but let's see. For gradient descent to converge, we only require that the gradient is an unbiased estimate of the two gradients. In fact, the term in GD is an empirical estimate of the expected value of the gradient. Any other unbiased empirical estimate of the expected value, for example, using any subsample of the data would suffice. Hmm. Just English on this slide. Okay, now I think this is just trying to tell why a stochastic gradient descent is nice. How to choose batch size? Okay, this is I think this is when you're trying to use a mini batch. I mean, the best way to find the gradient is simply iterate over all n, not n, we used m, no? So all m examples and you'll get your gradient. But that might be computationally expensive, so we're using batches. You keep taking b number of data points and find, why am I saying gradient? Theta naught and theta 1 using gradient descent method. So how to choose batch size? It's like until you suffocate your GPU, keep picking data sets. That is what it's trying to tell. Oh my goodness. Where was I again? I was here. No derivative. Okay. Hmm. Oh yeah, these were the terminating conditions, right? X values do not change, the function values do not change, or the gradient is almost zero. But if you reach a terminal point, it doesn't mean your point that you, uh, the point that you reach that is the global optimum. There's no guarantee. Okay, so there's a solution. You have multiple starting points. Fine, because your starting point ultimately decides at which pit you're going to fall. If you start here, you will go and fall here. If you start here, you'll go and fall here. If you start, let's say, here, or wait, let's say you start here, you may go fall here somewhere behind this mountain, but you would never reach here and here. So it depends. Your starting point will decide in which pit you're going to go and fall into. So here, there's one solution, no? Just do the same process but with multiple starting points. and then maybe you'll get a better idea as to where is the global optimum, minimum in this case. Subgradient. What happens when function is convex but not differentiable? So basically, if the function looks like it, this is a convex function, but it's not differentiable at these 2 points. It's a convex function, but it's not differentiable. So they're like, what happens is what's going to happen? Like, what do we do when this case appears? They're like concept of subgradient. Let's see, gradients of convex functions. For differentiable convex function, its gradients yield linear underestimators. Fine, maybe underestimators because it's below g. That's why it's called underestimator. I suppose basically a tangent line. But let's see, gradients of convex functions. Yeah, yes, I know. Fine, we get it. We get it. Fine. If the slope of the tangent is zero, it means you reach the global optimum for a convex function. We were talking about when it's not differentiable, right? Here it's not differentiable. So for convex non-differentiable function, we can define subgradients of, okay, fine. So it's like when this is there, you can keep drawing tangents. So on the left hand side, you will have one tangent. From the right hand side, you will have one more tangent. So these two are extreme tangents. And in between, I can draw how many ever lines I want passing through this. I can draw infinitely many lines that pass through the point and in between these two extreme lines. So what they're trying to tell is any of these blue color lines are subgradients. That's it. So all of those are subgradients. I think it looks like that. So any of those two. I mean, you have. I think that is what they're trying to tell. You have infinitely many subgradients. But let's see. F of x is greater than or equal to f of x star. X star is here, the point that we have a problem at. G is the gradient. X1 is x star. Hmm, I think that is what it's trying to tell. Any gradient, not any gradient, any line that is passing through this point of non-differentiability, and if it's in between these two extreme lines, then it's a subgradient. Maybe that is, yeah, I think yes, that's it. But this condition, what is this condition trying to say? F of x is greater than or equal to, yes. So basically, uh, wait, what is this? This was our function, no? It came like this, came like this, or whatever. Let's make this. This is not differentiable. One tangent is like this, another tangent is like this. So I can draw. So let me take one subgradient. This is one subgradient. So my f of x value will always be greater than any value on the subgradient. So f of x is greater than or equal to f of x star plus gradient of something. What? Let me see. Let's say if this is x. If this is x and this is x star, gradient of x minus x star. Hmm, Maybe uh, how do I mention? How do I represent this? Fine, we'll come back to this later, or should I just let me just take 2 minutes? Let me see. Gradient of, oh, it's not gradient of, it is gradient times this. So that's the problem. It's not gradient of. It's not gradient of. It's any vector g. Fine. G is just some random vector. Fine. I was breaking my head for no reason. G is any vector. Fine. So I'll show you what is happening. I was breaking my head for no reason. There is some function that's not differentiable. Let's call it f of x. It is convex, but then, and the subgradient at x star. So x star is the problem where is the point where we have a problem. So let me call this x star, and let me take some random x value, and here my tangent will look like this. LHS, RHS, my tangent will look like this. So my tangent should lie in between, my subgradient or whatever should lie here somewhere. So I'll draw something like this. This is associated with some vector g. Maybe g is the direction of this. I'm assuming g is the direction of this uh, tangent. I'm assuming. So fine. F of x is greater than f of x star plus this direction times the difference. I think that is what it's trying to do. So f of x star is here. You have the direction times the difference, so it will take you to this place. So this place will always be below f of x. So that is what it's trying to tell. Uh, this represents the new point on the subgradient, and f of x will always be uh, greater than the function value that any point on the subgradient has. See, for a convex function, if you draw the if you draw the tangent, all the values on the tangent will lie below the function. So similarly, even the subgradient points will lie below the function. That is what this condition is telling you. That's it. It is just representation. I was trying to see how did we come about this. That's it. Suppose we have a non-differentiable function. Fine. Subgradient descent is almost identical to gradient descent, except we use subgradients. Fine. So you have starting point x0. You keep iterating until convergence. Calculate subgradient. This is basically uh, the class of all subgradients. Because you have infinitely many subgradients, just take some random subgradient. Or maybe you could just take the subgradient that is exactly in between these two. You could do that as well. Calculate step size, move in the opposite direction because gradient descent. Fine. So G is the direction. G is the direction of the subgradient. Nice. Not gradient but subgradient here. Okay, no derivative. They're like, can we solve all of this without using any derivatives? Let's see. Particle swarm optimization. Okay, we were thinking about this, right? We start from multiple places, multiple starting points, so that reaching optimal point is guaranteed. Let's see. Communication between searching agents. Okay, communication. Now multiple starting points are communicating with one another. Let's see how that is done. Generic kth iteration. Let's say we are in the kth iteration. Let's see. One additional step. Maintain the best solution obtained so far over iterations. Okay, there's something called local best, and it's storing something. Best solution so far at any stage found by a search agent. Search agents are the, the starting points basically. At multiple starting points, you deploy something called search agents. So basically, the places from where you are searching. That's it. You can think of these honeybees as your search agents. Mm, Given f of x, and you have starting not starting point now. You are in the kth iteration, so you have xk. Select direction p. You can use gradient descent or whatever. We'll see. Is there any other method? It's the same procedure, but the only difference is you're storing something here. The best solution so far. If you remember knapsack, is it knapsack? What was it? What was it called? Uh, Integer. I think knapsack. Branch and bound. Yes, in branch and bound also we'll store the global best, something like that. So here we are storing local. There is a local best there as well. So maybe similar to that, but we'll see. We'll see. Maybe example will be better. Okay, yes. So we do have a global best as well. So local best is for a search agent, you will store the best solution found by the search agent so far. That is local best. Global best is the best out of all the local bests. That is the global best. So you have this. It looks like this because you have like one, two, three, four, five, six, around six, seven search agents searching. You have six, seven starting points where you deployed your search agents. They're searching through the graph for the global minimum or global optimum, and the best out of the local bests will be the global best. Particle swarm optimization. It's called particle swarm because you're deploying multiple search agents at multiple starting points. Yes, we will see. I think there will be a slide about how to choose the starting points and things. We will see. Okay, what is this? Next search direction based on the agent's own local best and overall global best. Fine. So we have to find the direction pk, right? So they're telling we will not find the derivative. Depending on the global best and the local best, they will decide the direction. So no gradient will be involved. We'll see how they will do that. That is why no derivative. The slide is called no derivative. This PPT. Okay, so there are three factors that affect the direction, and none of them use gradient. That's why no gradient. So direction of pk is dependent on the previous direction. Fine. So that is pik minus 1. You have multiple particles, right? So this is the ith particle, the direction of the ith particle, but the previous direction, k minus 1. direction from the current xi towards the local west. So let's say you are at, let's say the ith particle is at xk now, xik, and let's say its local best was local, so it's the ith local best, it's somewhere over here. So direction is basically the difference between them. So direction, what is the final point? Final is this is just vector at this point. X is a vector, right? X is a vector. So this will be, you will find this in the equation as well. We'll see. Oh, it's here. It's here. See, it is here. See. So the vector is there. Final point minus initial point will give you the direction from initial point to final point. So this is a vector that will uh, that will show me, give me this direction. Direction from xik by particle I towards global west. So if I am at xik and my global best is at global best is not dependent on the part, it's like the best of everyone, so it won't have I, it will simply have a global best. It's a global best for all particles, so it doesn't matter if it's first particle, second particle, ith particle, doesn't matter. This vector will be represented by xgb minus xk, and they've written it nice. So you have three factors. One is the previous direction, the other is direction towards the local best, the other is the direction towards the global best. And then you have some constant. So phi is the constant, some constant that decides uh, how much should the previous direction affect the current direction. You have C1 and C2, which are also constants, which will decide how much should the local best affect the current direction, how much should the global best decide the current direction. R1 and R2 are some random numbers which will lie in between 0 to 1. We'll see how all of this comes to be. Okay, fine. So they've given names as well. Inertia, because inertia is basically the uh, let's say you're moving. So since you're moving, in the next second you will tend to move because you were moving before. So it's like, you know, inertia, right? I don't have to tell what inertia is. The previous state will affect the current state. So that is inertia in one way. If you're moving, you will remain moving. So if you are in some pk minus one direction, you will tend to remain in that direction. That's why the previous direction is affecting you. Personal influence is basically you have a local best and you want to go in that direction. So you're being influenced that way. So personal influence. Social influences, there is some best value that is like it's applicable to all, it's the best of all things, so you want to go in that direction, you want to go in the direction that is like the best, it's like the best of the best. That is social influence, you want to go in the direction that is the best that everyone has found. Isn't this what all of us are doing? Social influence. Anyways, so inertia makes the particle move in the same direction. Personal influence improves the individual, makes the particle. Okay, nice, nice. So okay, fine. So here x is replaced with v. So v is velocity. If x is there, it is direction. If v is there, it's velocity. Now you might think, why am I adding position and velocity? It is simple. See, velocity is what? This one, right? So I this is nothing but uh, approximately for small values, I can write it as this. So if my delta t is just 1 second, it is going to be 1. So x2 is nothing but, okay, let me write delta t for now. X2 is nothing but x1 plus delta tv. Here, if you notice, delta t is t plus 1 minus t, which is 1. So that's why x2, or x2 in the sense you can simplify to xt plus 1. It's nothing but xt plus delta t is 1. So v of, maybe this should make sense. This is just there to tell you why am I adding x plus v. Because there is t as well, but t is 1, so you can't see 1. 1 is 1. Okay, so we have velocity changing, we have position changing. Fine. So the search agents are moving with a certain velocity. Interesting. R1 and R2 will be in between 0 and 1. They're random. R for random. Okay, nice. Are there examples? Okay, so this is nice. Nice. So yeah, personal best, there is global best. Yeah, velocity. So all of this will, and previous direction, where's the previous direction? It will also decide wherever is the previous direction, that will also decide where to go. Where should the particle go, that will decide. Okay. There's an example, f of x is equal to x into x minus x. This is a convex function. You can plot it and see. It will look like this. Uh, x squared minus 8x. This is nothing but x squared minus 8x. So fine. I mean, I don't have to follow that. So at 0 and 8, right? Yes. This is how it's going. It's a convex function. Consider a small swarm of particles. It's a single dimension function because you only have one variable. Okay, you have particles 1, 2, 3, 4. Their starting points. Okay, let me keep the graph. Is there a graph? Did they draw it? Okay, they drew it for me. I don't have to. You have starting points, and then you have velocities as well. How did we get these numbers? They're just there. You just randomize the numbers. Somehow just give the numbers. Now that you have your x values, if I substitute this in f of x, I will get my f of x values. So currently, if you notice, since the search agents, the particles basically, they did not start their journey yet, the current position will be the best position. So the local best will be wherever they are. So for particle 1, minus 7 is the local best currently. 20 is the local best. 9 is the local best. 84 is the local best. Because they did not look at any other point because time is 0. Uh, so global best will be the best of all the local bests. So minus 7 is the global best. That's why local best is their current xi values. In the sense, not f of x, but uh, uh, the x value corresponding to the minimum f of x, that will be stored in p local best. We are not storing f local best. We are storing the position local best. So we will be storing xi values, not f of x values. So we are not storing minus 7. We are storing 7. We are storing 7. We are not storing f of x. We are storing the position values. So if you plot it, it will look like this. So 7 minus 2, 9, 6. 7 minus 2, 9. So these are my four search agents, they will be searching the graph for the optimal point, which is here. They have to finally reach it. Let's see. So if you apply the formula for each particle, we'll get to know the new velocity and new position. New velocity we'll get from here. New position we'll get from here. And C1, C2 and all, they should only decide. We are not going to decide. Even the values of R1 and R2 are random. We don't get to decide. So maybe it will be given in the question. Or if they don't give it, then we should only decide what it is. Most probably they will give it, because if everyone chooses their own numbers, then it will be difficult for them to correct as well. So they will, if they're asking us to do this, they will give us the R values as well. And the R values usually change from particle to particle, so it's not going to remain constant. But C1 and C2 will remain constant, phi will also remain constant. Only R1 and R2 are random numbers which uh, keep shifting, but they will lie in between 0 and 1. That is fine. So particle 1, if you substitute, you'll get your new velocity. These are old values, right? We will get new values. Where are the new values? Okay, I see a new term here, fitness. Fitness is basically uh, the function value. That's it. Fitness is basically the function value. We want to minimize fitness in that sense. Minimize fitness. Particle 3, particle 4. Fine. So this is the new table at t is equal to 1. So basically our first iteration. In the brackets we have the previous positions and previous velocities and previous function values. So best local best, previously we had -7. Currently we have 4.25, which is lower. -7 is lower. So the x value corresponding to -7 is the local best, which is 7, which was in the previous iteration. -2.31, 20, which is lower, -2.31. So what is the x value corresponding to it? 7.7. So my local best will be updated from it was initially uh, it was initially what, -2. Now my local best will be 7.7, because its function value is lower than 20. Same is the story for other things. -8.16, so my local best will be 6.8, which is lower. -15 is lower, so its x value is corresponding x value is 3.7. So 3.7 will be my local best. Global best is it corresponds to that x value whose f of x is the least among all f of x's. So the least so obtained is -15.91. We did not get lower than this in any of the iterations. So that the x value corresponding to that is 3.7. So 3.7 is my global best for the next iteration. Now that I have to find the next. I mean, you don't have to write this as well. It's the local best. For every agent, you have local best. For all of the agents, you have one global best. If you look at the calculations previously, the local best, the global best, uh, we had a global best, but local best is basically the same x values. So the personal influence will be 0 in this first iteration, because local best is the current value. There is no other value. But we did have social influence. Social influence was non-zero in some cases. Here, social influence is non-zero. Social influence non-zero. Social influence non-zero. But this is zero. In the first iteration, that will pakka be zero, because local best is the current value. You fine. Okay. Can we find we do we have okay fine. So time t equal to 1, it change to this. If you keep repeating the process, all my particles will move in one direction, which not one direction, but all my directions will converge to a certain point, and that will be close to the uh, global optimum. So how do I find the global optimum? Just in whichever iteration I am, I will just look at the position of the global best, and its corresponding f value will give me the fitness. If this is least, it means we are happy, we are good to go. That's it. There is not much theory to this. This is how we do iterations, though. Important. Just in case. I mean, you could, if you've understood the concept, you can write inertia plus personal influence plus social influence, and then you just have the how do I find the next position? You have this. Mm, fine. So this is like one example. There is a graph. I think this is supposed to be an animation. I think yeah, this was supposed to be an animation. So just look into it. It's like all these X marks, all these crosses will move around and stop in uh, local optimum. You have many local optimum, and then you have this dark blue, which is the global optimum. So all these X's will keep moving, and they will stagnate after some time because they can't move. After they fall into a pit, they can't move, right? So that is how it is. Oh, it was this one. Optimization of a nonlinear function with equality constraints. Okay, let's see what is this about. Non-linear programming. You have some objective function. You have. Did I open the right slide though? 24, 23. Yes, I think I did open. Yes, yes. Okay, you have some objective function. You have equality constraints, inequality constraints. My x is of n dimensions. F is a scalar function. Hi and gj are also scalar functions. And number of equality constraints are less than n. What is n here? Okay, n is a number of dimensions. Fine. So if I have five equality constraints, it means my dimension should be more than five. Fine. If I have a three, if I have a three-dimension problem, then number of equality constraints should be less than or equal to three. Fine. Example: minimize some objective function. It is non-linear. They gave one equality constraint, one inequality constraint. That's it. This is one non-linear programming problem. Non-linear programming problem with equality constraints. Okay, if you remove the inequality constraints, it becomes non-linear programming with equality constraints. This is one example. Okay, Lagrange multipliers. Find an equivalent unconstrained optimization problem by introducing Lagrange multipliers. Okay, let's see what is this going to do. Minimize a function, and then you have some set of equality constraints. So what do you do now? I can rewrite this entire thing as this, basically by defining something called the Lagrangian. The Lagrangian is a function of x and lambda. So x in the sense your input. So It's like x1 comma x2 comma x3 and so on. It's an input irrespective of the dimensions. So f of x minus lambda times constraints and sum them up. You want to minimize this. So okay, Lagrangian is basically a function of x and lambda. It is defined to be f of x minus uh, all the constraints, but the constraints are multiplied with the lambda. They're not the same lambda, so lambda 1, lambda 2, lambda 3, depending on how many other constraints you have. Sum them up and just take the difference. This is defined to be Lagrangian, and they're telling us to minimize this. Now, if you notice, there are no constraints here, so this is an unconstrained problem. Apparently, these two are equal. Solving this constrained problem with equality constraints and solving this problem, the Lagrangian problem, with no constraints. It's an unconstrained problem. These two are equivalent. Are there examples? Okay, fine. Example is here. You have a non-linear function and then you have an equality constraint. So first I will define what is my Lagrangian. It is my function. I have a function minus lambda times each constraint and then I just add all of them. Here I only have one constraint, so I have only one lambda, x1 plus x2 minus 6. It's fine. Since this is an equality, it shouldn't matter if I write it this way as well. Since this is an equality, so you have no problem. So it doesn't matter if there's a plus here as well. Shouldn't matter. You'll get the same answer. But just mention minus. And it looks nice if x1 and x2 has no minus sign. So we prefer writing it this way. That's it. But it shouldn't matter. It wouldn't matter as well. In exam, I don't think you lose marks. Since these are equality constraints. So minus or plus, it shouldn't matter. It shouldn't matter. As I was telling, x in this case is x1 and x2. So it is a function of three variables here. So here x is in bold, right? So wherever you see bold, it means it's a vector. A vector has components. In this case, x1 and x2 are its components. So fine, this is how you rewrite a non-linear programming problem with equality constraints in terms of the Lagrangian. Minimize the Lagrangian. That is the equivalent problem. Okay, and now I think we're going to see how do we solve this Lagrangian problem. So if you have a non-linear program, meaning problem, non-linear programming problem, with equality constraints, I can rewrite it using the Lagrangian of it, and my new problem is now minimize the Lagrangian. So let's see. First order necessary condition of optimality. Optimal solution next star of the problem. Okay, now it's telling that if I take the derivative of the Lagrangian, then at the optimal solution, this should be 0. In other words, if I equate the Lagrangian to 0, whatever solution I get should be the optimal solution. So I will take the derivative of this Lagrangian. So I'll get gradient of f. Here lambdas are all scalars, so they should not affect me. So directly I'll get gradient of h. So gradient of Lagrangian is basically this. If I equate it to 0 and solve for x, I should get my optimal solution. Oh, it said necessary but not sufficient. Fine. But if it's an optimal solution, it should satisfy this equation. If x is optimal, it should satisfy this equation. Okay, there's some example here. Given a constrained optimization problem in two variables and one linear equality constraint. Fine. Now I just have to convert this to my Lagrangian. So my new problem is now minimize Lagrangian. There are no constraints here because now the constraint has become a part of the objective function. So there are no constraints. So this is one objective function, no constraints. So how do you solve this? I was like, you take the gradient, right? Gradient of the Lagrangian. So just take the gradient of the Lagrangian with respect to all the variables. So here x is in bold, so it is telling it's a vector. So essentially x1, x2, and lambda. So take partial derivative of the Lagrangian with respect to lambda, x1, and x2, and equate all of them to 0. So you will get three equations, which we did here. You got three equations. So if you differentiate with respect to lambda, what will you get? This will become 0. You get x1 plus, okay, you'll get this one. If you differentiate with respect to x1, you will get x2 minus lambda, which is this one, and this is this one. If you solve this, you will get, you have three variables, x1, x2, lambda. You have three equations. You can solve it. You will get x1, you'll get x2, you'll get lambda as well. But lambda, it's fine. Lambda is there. You don't have to find lambda unless they ask you. Because the final solution is essentially x1 comma x2. So that will be your optimal solution. Why is that? Because of Lagrange's condition. Optimal solution must satisfy the first order condition, which is gradient of Lagrangian is 0. Okay, we have more examples, I suppose. Okay, you have a new function. You want to minimize this. You have an equality constraint. Now, how do we solve this? Just convert it to Lagrangian. After converting it to Lagrangian, just take the derivative with respect to each of the variables, x1, x2, and lambda. Equate them to 0. You'll get three equations. You have three variables. You can solve all of them. You will get x1, x2, and lambda. Okay, this is another example. You have a nonlinear function. You have two equality constraints. Since you have two equality constraints, in your Lagrangian, you will get two lambdas. You get lambda 1, get lambda 2. This is your summation of lambda I h I. Summation lambda I h I. This is what is happening. You take minus because you want to subtract it from f of x. This is your f of x. Now do partial. Okay, now Lagrangian is a function of four x1 x2 four variables x1 x2 lambda 1 and lambda 2. So you'll get four equations. You have four unknowns. You can solve it. You will get your x1 and x2. You'll get lambda 1 and lambda 2 as well, but final solution is x1 comma x2. Okay, now they're giving us a general representation. X is a point of n-dimensional point. You have m equality constraints. Objective function is f of x, which you want to minimize, and then you have many equality constraints. The Lagrangian of this is basically f of x minus summation of lambda I x lambda I h I. In this sense, you have to here all constants are there, right? Take them to the LHS, so it will become h1x minus b1, h2x minus b2. Finally, what you should get is you have to get something equal to 0. Something equal to 0. That's why we are sending the b's to the LHS. So this will fall here. So lambda 1 h1x minus b1, lambda 2 h2x minus b2, and lambda m hmx minus bm. We are doing this because we want equal to 0. That is the reason. That's it. Now that you have your Lagrangian is now a function of how many variables? X has how many? X has n components because x1, x2, xn, you have n components. And lambda, how many lambdas do we have? Lambda 1, lambda 2, lambda m. So you have m lambdas. So you'll get n plus m equations, I suppose. Yes, so you will get n plus m equations to solve. And you have n plus m variables. The n variables are x1, x2 until xn, and the m variables are lambda 1, lambda 2 until lambda m. N plus 1 variables, n plus 1 equations, you can solve them. N plus m equations, n plus m variables, you can solve them. Mm, derivatives with respect to Lagrange multipliers. Okay, the lambdas are called Lagrange multipliers. The lambdas have a name, they're called Lagrange multipliers. Mm, okay, so primal feasibility condition. So if you look at it, the constraints as they are the main constraint. Like in the original question, you have constraints, right? Equality constraints. So the here you when you're trying to differentiate the Lagrangian with respect to lambda 1, lambda 2, and so on, you're getting the equality constraints back. You're getting the equality constraints back. The same thing. Why? See, if you differentiate this with lambda 1, this is going to be 0. All of this is going to be 0. This is going to be 0, and all of this is going to be 0. Because lambda 1 is only here, lambda 1 is nowhere. So you're getting your equality constraint back. So the set of the equality constraints, all of this is called primal feasibility condition. So basically, the equality constraints which we originally had, those are called, if I just collect them and put them in one place, that is called primal feasibility condition. The set of all equality constraints, that is the primal feasibility condition. How did we get them? We got them back because we were trying to solve how many equations do we have? We have m equations here. When we are trying to solve them, we got our equality constraints back. This is the primal feasibility condition. Do we have other conditions? Derivatives with respect to Lagrange multipliers are same as the constraints. Yes, if you differentiate Lagrangian with respect to Lagrangian multipliers, you're getting the constraints themselves, the equality constraints. Primal feasibility. Yes, primal feasibility. This is what I was talking about. The set of all these equations, it is called primal feasibility condition. Derivatives with respect to input variables. Okay, so differentiating the Lagrangian with respect to x1, x2, x3, and so on. What do you get? Our Lagrangian was something like f of x. Fine, I'll just write. If you differentiate this with respect to x1, you get something from here, you get something from here, you get something from here, you get something from everywhere. So what is that something? Yes. So from This is nothing but d by dxi of f of x minus summation lambda. Since I is already used, I will use j h of j minus b. So if I apply the derivative, I'll get dou f by dou x. Lambda is constant will come out, and b is okay. So this will go away because it's a constant. So finally, I will get this. So what is this? This is the Lagrangian with respect to x1, x2, x3, and so on. And you equate them to zero, right? So they're telling if we write in matrix form. So if you collect all of those equations and put them in a matrix, you'll get matrix form. So which can be simply written in one line, which is this one. The gradient of f of x minus summation of lambda j's times gradient of h of x. We got this by taking the derivative of the Lagrangian with respect to x1, x2, x3, and so on. This is dual feasibility. Primal feasibility are just the equality constraints themselves. Dual feasibility is this equation. This is an equation in matrix form. So within this matrix, you have multiple equations. How many how many equations do we have here? We have n equations. All of them are represented using this one single matrix. Okay, solution techniques. How do we solve it? Uh, Solving what? We were solving non-linear problems, right? Non-linear programming problems. Lagrange multiplier method we've just seen. There are other methods as well. We will see. I think all of them will be in the slides to come. Since it's 1 p.m. now, I will stop here now. I will continue after the physics quiz is done. So let's see. Let me stop the live. Meet you after the physics quiz. Where's this?